Welcome to first course on power systems, and we are talking about module 4, which is on calculation of power flow on power system networks. And like our other modules, this module is also very connected to this reference textbook. So in this particular module, we'll see how we can calculate this power flow in our power system network. And first we have to describe the system, which we'll do. And then we'll take an example of this 3-bus power system that we have seen earlier in module number 3, our initial module, I would say. Then we'll build this admittance matrix, and we will write the basic power flow equations, and we will solve it using this Newton-Raphson procedure. And also we'll look at how we can extend this to fast decoupled Newton-Raphson and sensitivity analysis, and what happens when we reach VAR limit on one of the buses or more than one buses. Okay, so those are the things which we'll look at in this particular module. So first of all, why do we need to calculate power flow? Well, we need this for planning and operational purposes. So this is a very commonly done thing in utilities, and also it's needed for contingency analysis. If one of the lines were to fail, how would this power be flowing on other transmission lines? So that can be predicted using a power flow analysis of this sort. And it is also needed as an initial step in short circuit studies as well as transient stability studies. Okay, so it's a very important part of any power systems course. So as far as the system representation is concerned in calculating this power flow, we'll assume the bulk power system. That is, we are dealing with a transmission level power system, but it's implied that underneath we have a distribution system. Okay, and then we'll assume that it's a balanced three-phase system, and therefore we can, I should change the color of this pen here. Let me just do this very quickly here. We'll assume that it's a balanced three-phase system, so we can model it on a per-phase basis. So that's what we'll do. When it comes to transmission lines and how to represent them, we can treat them as long lines and have lumped models for those long lines with all its accuracy. But in our example, we'll just treat them as a medium length line where we have the series inductance and resistance in series over here, and then we'll take the complete capacitance of the line and put half of it over here and half of it over here. When it comes to transformers, we can represent them by their leakage impedances in per unit, because most of this calculation is done in per unit. So we can represent this transformer leakage reactance and resistance in per unit and neglect the magnetizing current of them. And if they have the nominal turns ratio, then per unit, that nominal turns ratio disappears. Okay, and when it comes to this load can be modeled as P and Q, power and reactive power, or it could be modeled through a current source, constant current source, or as a constant impedance. Okay, so there are a combination of those three. Right. Now, in terms of describing this power system, we'll say that we have different types of buses. Those are listed here. Buses where loads are connected, I'm not sure why it turns to green by itself, but that's okay. Where load is connected, we'll call them PQ buses, because that's where we specify power and reactive power that this load is drawing. Buses at which generators are connected, we'll call them PV buses, because that's where the power which is being supplied by the generator is specified, as well as the voltage magnitude specified. So we'll call them PV buses. And then in any power system that we are trying to do calculations on, there should be one slack bus. And the purpose of this slack bus is that we don't know ahead of time how much power, real power, and reactive power is needed. Okay, and this bus, which is sometimes also called infinite bus, can supply whatever is needed. So we need one of them like that. And then sometimes to represent transformers and so forth, we need an additional bus, and we can think of it as a PQ bus with P being 0 and Q being 0 on that bus. Okay, so that pretty much covers all the types of buses that one would encounter in these systems. And here we are looking at this example of 3-bus that we have had before, and we are at this 345 kV. And here you see that on this bus 1 is the slack bus we have picked. Okay, and this bus 1 is connected to other 2 buses with these transmission lines. Here a generator is connected, so it's a PV bus, and here a load is connected, so it's a PQ bus. So we have all the 3 types of buses that we need in this example. All right. So when it comes to modeling these transmission lines in this power flow program, we will go to this module 3, where we saw this table 4-1 in chapter 4 of our reference book. And for 345 kV line, the series reactance and series resistance, they are given, and the shunt capacitance per kilometer, that's given. And then in order to represent them on a per unit basis, we need to calculate this impedance base. And this impedance base, the voltage line to line, of course, is 345 kV, but conventionally, the MVA base is chosen to be 100 MVA on a 3-phase basis. So on that, this base impedance turns out to be about 1190 ohms, and the base value for the admittance then is just 1 over the impedance. So using that, we can take the information given by this on transmission lines, and we can calculate the impedance of these 3 lines from 1 to 2, 1 to 3, 2 to 3 in ohms as well as per unit. And similarly, we can do that for susceptances in micromhos or in per unit. This symbol mho doesn't come through, but wherever you see this box, that's what is implied. Okay, so with that, we will proceed to build this admittance matrix. To build this admittance matrix, you see here all these lines are, of course, represented by the series impedance and their susceptances. But we will assume that we have 3 currents going into these buses, I1, I2, and I3 here. So, this is for any n-bus system. So at bus K, the current that is going in into that bus K is this voltage at that bus times all the admittances that are connected from that bus K to ground. This YKG is from bus K to ground, plus the currents those are going out on the transmission lines that are connected to bus K. So VK minus some other bus M, V sub M, divided by the series impedance of that bus, right? Where this M can vary from 1 to N, depending upon how many transmission lines are connected, except M cannot be equal to K, like this here. So we can take this expression for the current and then rewrite it in this form, where all the terms connected to V sub k are in this bracket over here, and the rest are over here, like this. So here you can say that the quantities within this bracket here, they are ykk, and they consist of these two here terms, whereas ykm over here is one minus, this minus sign is included here, 1 over zkm over here, right? So with this, using, again, repeating this ykk and ykm here, we can then write this admittance matrix for all n buses that we have in the system. So on the right-hand side, you have the voltages here, and on the left-hand side, we have the currents, and they're related by this admittance matrix, right?